our, approximate our, what is the reward that we are getting for any state or any action that we take in terms of a deep neural network. Okay. We will take a closer look at this when we are talking about policies. For now, let's move ahead. So there are different types of policies that I wanted to introduce to you. One is the lookup table that we have seen already in the case of our grid world. The policies can be polynomials, or it also can be deep neural networks. We'll try to see what these means and how, why, or where do we use any of these, right? Great. Now let's actually talk about agents so that we are able to, figure out how our policies are being trained. So yeah, so typically whenever I say agent, first thing is the James Bond agent, but yeah, we are not talking about that agent. We are trying to talk about the reinforcement learning agent. So let's try to see if we are as good as the 007 up here, right? So the thing is, how do we go about training our agent, right? That becomes very important. So there are a couple of things that we have to identify. We say reinforcement learning algorithms can be of three types: value-based, policy-based, or actor and critic. Let's take a look at what these mean. Okay. Value-based is, as we saw, we identify what is the reward. We try to figure out what is the reward. And based on that, after identifying what the rewards might be, then we try to extract a policy out of it. Okay. So you can take an example of, you can figure out what's happening in either of these cases. First, we try to figure out what is the reward for any state or any action that we are going to make. And based on that, we extracted a policy, right? Like our Q learning method, wherein we created a table, we figured out what are the rewards for different states and actions. And based on that, we extracted a policy for us, right? In this particular case. Now, just to put it in terms of functional mapping, so what we have is we have a function which is going to say for any action in any state is going to give me a reward value, correct? Or we can call it as quality, cumulative reward. It's going to be cumulative reward. So let me find an eraser for myself, right? So we will be getting a cumulative reward, and we are trying to find a functional mapping so that we can predict what is going to be the cumulative reward. Okay. Now, once you have identified a function which is able to do this correctly, then what you can do is you can use this to predict what would be the reward for any of these states and then come out with a policy. Okay. And the policy is nothing but a function which is going to map observations with actions, right? So whenever there is an observation, the policy would figure out what action to take, and this should be giving the maximum reward. Okay. I hope this is clear to everyone. So can you give me on a scale of 1 to 10 how clear you are with this? 10 being you're crystal clear with this right now, 1 being it is not at all clear. Can you quickly drop it in the chat window, everyone? So we are 40 people up over here. So please do let me know. I'm not expecting you to be at 10 for this. Anything above 5 and above would be really nice. And if you believe there is something that I should repeat or you want a little bit more clarity on, please do let me know. Anisha, can you please let me know which part is confusing as of right now? Cumulative reward. Okay. So the thing is, in reinforcement learning, thank you for asking that question, Anisha. So let me put it like this. The thing is, in reinforcement learning, what we are trying to do is we are trying to identify the actions which would set of actions which would lead to maximum reward, correct? So at any state, for example, at this particular state, I would have reached this particular state from somewhere, correct? So if I'm at this particular state, I would have already received some amount of reward. Now my objective is to identify the action which would give me the maximum reward, correct? Maximum cumulative reward. So I can either go here, here, or here, right? So what it will try to do is it will try to identify or predict, if I go here, what might be my cumulative reward then. If I go here, what might be my cumulative reward here, and similarly for here. And then based on these predictions, what it will do is it will choose the one which will give the maximum cumulative reward. Let's assume it chose this. Okay, it chose to go up. So if when it goes up, it is getting some reward, actual reward from the environment, correct? The environment is going to give it -1. Now the problem is, once it goes through this particular path and it takes some path, it will figure out, hey, this was not the best path possible for me. Because whatever I was predicting as my cumulative reward is not matching the actual reward that I'm getting from the system. So for that, I made a wrong decision somewhere, correct? So based on that, it will come back and redo this and now take the different path. And now it will get a better reward. Is that clear, Anisha, now? Is it better? Okay, awesome. Thank you. Let's move ahead now. Now, the problem with a value-based approach is it's typically suitable for very small and finite or discrete action spaces. But the problem is it cannot run for something which has lot many states, and we are not talking about mapping our observations to actions. So the problem is it will not be able to work in any other setup of a grid world except for this one, right? If I put any other grid world setup, it is not going to work out there because it doesn't know why the action is giving it, the best reward, because we never looked out for policy. Policy was the afterthought for us. We try to first identify what are the rewards and then extract a policy based on that value. That's it, right? Now, on the contrary, oh, right before that, so the way that we estimate the Q values for every next action that we are going to take is based on this formula, which is known as based on Bellman's equation. So if you notice, this is a recursive equation and recursive formula wherein the previous estimate is actually required to figure out what is the next state or next action we should take. So this is just for our understanding. I'm not going to go deep into Bellman's equation, but if now anybody asks you what is the fundamental of Q learning or what is the fundamental equation that is governing Q learning, you should be in a better position to say Bellman's equation, at least even if you are not aware of what or how it is working around, right? So this is very famous and common in most of the Q learning or value-based RL algorithms. Okay, whether it is Q learning, deep network, or DDPG, deep deterministic policy gradient, etc. It actually works in all of these. Now comes the policy-based. Now in this, the difference is instead of focusing on rewards, our focus is on the policy. What we are trying to do is we are trying to find a mapping which can correlate observations and actions, right? And this function would have certain parameters, and during the learning process, we are trying to tune these parameters so that we are able to map it properly. And the quality of this mapping, in terms of curve fitting, we call it as goodness of fit, right? Something similar out here. The quality of our mapping is determined by the reward that the system is going to give. Okay. So the thing is, I think, I hope we are clear with the difference from the value based. In value based, we were focused on reward. What is the reward we are going to get? In policy based, we are focused on what is the mapping between actions and observation, right? Great. So what is the trick out here is this process of learning wherein we are trying to tune the parameters, etc. Uh, it may become quite tedious because it's an optimization problem, right? So you have to kind of reiterate a lot of executions and figure out whether your policy is actually accurate or not, right? So you have to kind of execute what the current policy would give us an action, identify the rewards, see if any other action will actually give you, better rewards or not. So in that sense, what happens is you will be keeping on updating the policy, right? Based on some algorithm. It's usually gradient ascent method. So you identify a point wherein you try to get the maximum reward. Now the problem is, how do I ensure that I'm always getting the best possible or the global maxima, right? So these kind of problems come into picture. And it is a problem that usually people are working with in terms of changing the kind of optimization workflows that they use, to get this particular policy, which will give them the maximum reward. Now, the problem is, one of the biggest problem in this is this requires too many samples or too many trials, right? And if your process is complicated and computationally intensive, at that particular point of time, this may become unwieldy because it may take days for your system to identify a point of maximum where it will get maximum reward, right? So now people actually put their mind together. They were like, okay, this is not a great thing to happen because I'm ultimately trying to figure out what is the maxima of my reward, right? So is there a possible way wherein I am not only identifying a mapping or policy between states and observations, but I'm also trying to predict what my reward is going to be so that I don't have to blindly go in any direction. Rather, I can get a direction in terms of where or which direction I should optimize in. Correct? So that's where the actor and critic method came into picture. So by now you would have understood that most of the reinforcement learning problem statements are quite complicated and it requires deep neural networks to map things, right? If there are many states, it is quite convenient for us to use neural networks to map our or use as our universal function approximations, right? So now the whole idea is there are two neural networks in an actor critic method which are being simultaneously trained. So what does this mean, right? What does this mean? So the whole thing is there is this actor network. What this is trying to do is it is trying to figure out at every state what is the best action to take. It's only trying to learn at every state what is the best action to take. Whereas the critic is trying to estimate or predict for given observation or given state and action, what is the approximate estimated reward value? Okay, what is the estimated reward value, cumulative reward value? It is trying to predict that. And based on that, it will act as a guide to ensure that actor is making good decisions or taking good actions. Now, before I go ahead, is this clear to everyone or is it confusing? Can you let me know in the chat window if something is not clear at this portion? Because this is one of the most classic and most widely used kind of reinforcement learning algorithm or agents that you will be encountering. Okay, if you get any questions, please drop it in the chat. Okay. So the whole thing is, how does this work, right? Let's talk about the training process itself. So actor is going to identify or get these observations or states from our environment, correct? And according to its own internal mapping, it is going to say, okay, I'm going to make this action. I'm going to take this action, right? Now the thing is, the critic is also going to get these observations. It is going to observe what states are coming, what state the environment is in. It is going to observe what actions the actor is taking. And based on these two, it is going to make its own prediction of the reward value or the reward. Correct? Now, what happens is the value that it predicted, it will compare it with the actual reward that the environment is giving. Because environment will give its actual reward, correct? And the critic is trying to kind of predict that particular reward and it will compare it. So when it is comparing, it may have some error, correct? And now this error will cause the critic to actually tune itself or make itself better so that it is able to make or predict values or rewards better. Okay. Now, this is all about critic. The critic is actually now making sense, right? The critic is actually trying to predict what is going to be the cumulative reward. And based on what reward the system is sending it, it's trying to make itself better at prediction. But the point is, how do we update our actor, right? Actor also requires some sort of reward to come in, right? So what critic does is, whatever the reward value that critic is predicting, it is giving it as a reward to the actor. So what happens out here is, the actor is going to now learn or get better based on the value that is being predicted by the critic, right? So if you notice, the way actor is going to predict better is by updating itself based on the reward values critic is predicting. And critic is going to get better by predicting correct reward values. So in turn, it is kind of like, synergetic learning, right? Both of them have to become better, and only then they will be able to find proper mapping or find better, mapping which will give them the best reward possible. So before I go ahead, is this clear to everyone? On a scale of 1 to 10, can you quickly tell me if this is clear? Because we have a lot of things left to cover. I wanted to spend a lot of time in this one because if this is clear, everything else is something that you can follow. Everyone, can you please quickly drop it in the chat window if this is clear to you? It is totally fine if you are not on a 10 because it would be amazing if you're on a 10 right now. So can you quickly tell me if this is clear to all? Okay, I think everyone is here and listening. Great. So because of this, the critic or actor and critic method, it kind of removes the shortcomings of policy and value based method. So it actually brings the best of both worlds and is more sample efficient and also can learn stochastic policies, etc. So that's how the actor and critic method actually makes the training agent training or training of the agent much better. Okay. Now let's actually take a look at how our walking robot example can be implemented, right? That's what we wanted to actually achieve to begin with. So our objective was to make sure that our robot is walking on a straight line without falling down, correct? The first thing is environment. For environment, what we have used is, apologies, for environment, what we have used is Simulink. Simulink is a dynamic system simulation environment, which is a part of MATLAB, and it is a non-coding environment. The thing is, there we design the logic in terms of a flow diagram. So let's actually take a look at it. So if you notice, this is the model of the robot that we have created in Simulink, and we have used something known as Simscape as a part of Simulink to create this robot. So instead of writing equations, we have used some physical blocks, right? Like joints, solids, and connected them together with references to create our robot, right? So you can see there are joints, knee joint, hip joint, ankle joint. So the beauty is we are not working with equations anymore. We are working with more or less, physical system, physical units. And in terms of equations, if you notice out here, the equations are created or designed in terms of block diagrams. We'll take a closer look into it when we actually take a look at rewards. Okay. So our sensors are making almost 38 observations. So we are working with 38 observations in this case. Okay. Which is displacement in y direction, velocity in z direction, y direction, x direction, yaw, pitch, roll, angular velocities, what are the angle joints, angle speeds, angle torque, so many different things, right? So all of this actually becomes very easy when you're working with something which is which resembles quite well with what you're looking at in the real world, correct? That's where the Simulink comes into picture. So I'm not going to spend much time on to explaining what Simulink is because that is something that we can take a look at on a later stage. Right now, what I'm going to show you is how we are able to put it across, right, in a computational environment. The first step, which is one of the most important step, is to create the environment. Okay. Once that is done, the second most important step is designing the reward. Correct. So let's see how we design the reward for this particular robot. So the reward that we actually created is based on a paper. If you see, there is the author and the paper linked out here. So what we are trying to do up over here is we are trying to just a small second. I will have to. So what we are trying to do up over here is, if you notice, we are rewarding the robot for moving forward in the X direction, and for sustaining the motion, we are rewarding the robot. But we are also penalizing the robot for deviating from X direction, or falling down, or for using too much or making sudden movements, right? So this may look very simple, but this actually required a lot of researchers to come together and brainstorm and actually come up with this particular reward forming technique, right? So that is the reason I was saying reward formation is one of the most important aspects of reinforcement learning. Okay. Now the third portion is creating our policy. So in order to create policy, and if you're working with deep neural networks, which is going to be the most usual case, in MATLAB, you have something known as Deep Network Designer, which is an application, which is a part of MATLAB. Let me kind of reshare my screen so that I am able to show you what exactly it looks like. Let me know once you're able to see my screen. Great. I think you should be able to see my screen now. Let me navigate to my MATLAB. So in MATLAB, out there in applications per se, in this application section, you will see there are many graphical user interfaces or applications for you to interactively perform activities, right? So there is a application known as Deep Network Designer, which looks something like this and helps you to design your neural networks in an interactive format by dragging and dropping. So the whole thing is, you again do not have to code anything. You can directly drag and drop and change your hyperparameters and set up your networks, right, in an interactive format. So this becomes, or this makes your system quite fast and quite robust. So now finally you can create your reinforcement learning agent by just dragging and dropping a block and setting up everything. And to set up your agent, it is kind of like 6 lines of code. That's it. And you can set up your reinforcement learning agent. Mind it, this is very powerful, but at the same time, this is for standard problem statements. You also have flexibility to create your own agents, create your own networks, create your own training algorithms. But these are advanced topics, and you can also work with not one reinforcement learning agent. You can work with multiple reinforcement learning agents for the same problem. So it is typically useful when you have cluster of things, right? Like cluster of drones flying around, or some sort of multi-unit systems coming into picture. So if you're interested in that, do let me know. That is something that we can actually talk and send some information for, right? Great. So let's see what actually happened when we actually trained. When now, because we have set up everything, the only thing left is to train the agent, right? So initially, when we run the simulation, this is what we will see. You will see the robot is falling down. It's not even taking a single step. But then slowly and gradually, if you notice, it is moving its leg. After some iterations, it is now able to take a couple of steps, but still fall down, right? It's not able to maintain its motion. Now it is able to walk a little bit, but it is deviating from its, X line. So it is not walking straight. It is deviating. Now, after a little bit more training, it is able to walk okay, but it is having some weird action of walking, correct? Now, you will see it is still deviating, but it is much better than earlier, right? And in order to speed this up, you can always use parallelization and asynchronous parallelizations so that you can quickly train your robot, or any other system in your requirement interactively. So you do not have to, worry about anything else. So ultimately, when you train your robot completely, it will look something like this, wherein it is walking quite good in a possible straight line for a longer duration, right? And once you have done with all of this, the ultimate thing is you can directly put this algorithm or the policy that you have trained onto your choice of hardware without having to manually code anything. You can generate your C code or device code or CUDA codes if it is NVIDIA, devices, Jetson, Nano board, or something that you're working with. You can directly generate, production level codes and put it onto your hardware. And that is something that you can do with MATLAB and Simulink. Okay. And because this is something that I happen to be aware of, that's the reason I'm sharing with this. So just to wind up things, because we are coming to the end of our discussion, reinforcement learning is not only for robots or cars. It can be utilized for n number of application areas. It has been already being used for chemical process controls, for very complex plant level controls. It is being used for games, creating artificial intelligence systems for playing games. And mind it, a couple of these AI systems have already beaten the world champions in their respective games like chess, etc. It is changing the way prosthetics are working for people, right? It is able to make prosthetics which are tuned to your prosthetics, which are tuned to your needs and purposes. It is also working in effectively improving the efficiency of human controllers in a particular plant, because not all things can be automated, but reinforcement learning is bringing in that automation wherein human expertise is guiding the reinforcement learning agent to actually make correct decisions. So this is just getting started, and there are tons of new areas and avenues that you can explore. And if you are interested in bit more, I'm quite sure you have seen this, but just to emphasize, there are many examples, and we keep on adding some new examples all the time to ensure that you are getting some more advanced information on what different aspects of reinforcement learning that you can work with, right? So this can act as a template for you. So before we wind up, I want to talk about pros and cons of reinforcement learning, because that is very important. So the pros of reinforcement learning is you do not need to collect your data before training. You don't need to do that because it is an interaction based data. So it is going to take data as and when the things are going ahead, right? And thanks to our deep neural networks and possibility of working with these neural networks, we are now able to solve even complex problems using reinforcement learning, right? And we can find an end-to-end solution because we are not focused on only solving a problem and keeping it on our computers. Rather, we can actually put it on real life hardware and make it work in real world, right? And can be used for non-linear environments. We have seen that. The cons is it is very difficult to verify trained policies. It is, sample inefficient. It requires a lot of trials and errors. We have seen that it's a trial and error based method, and the number of design parameters that you may have to identify and tune is quite large, like for reward, for networks, for training hyperparameters. There are so many different things, right? Some ways by which we can help is by simulation. And let's see how MATLAB and Simulink can help you with this particular kind of simulation. You can reuse existing codes or models for environments. So you do not have to create your own environment from scratch. You can talk to us, or you can talk to your colleagues or research articles, and you will always find some models out there which you can use as environment. You can always use simulation to validate your policies, because in real life you may not be able to encounter these extreme scenarios. But by using simulations, you can actually simulate extreme scenarios and ensure that your system is actually working properly. You can always run your simulations in parallel. This is not going to reduce the inefficiency with respect to sample size, but it is at least going to improve the speed and reduce the time required for you to, do the training. Last but not the least, uh, there are so many examples and blogs and other things and expertise that we have within MathWorks and team, that we will be able to support you to actually find certain good parameters to start with. It may not be exactly what you need, but it is going to be a very good start for you to begin with. So you can actually take a look at different toolboxes and different examples to get started. So you will not be starting from a very blank slate. Rather, you will be able to work with something much more tangible. So I hope the key takeaways that we've discussed during the beginning is something clear to you. Now you should be in a better position to understand what reinforcement learning is, why is it important, and should you care about it. You can also figure out, how or what are the different elements associated to reinforcement learning. What are the different things that you need to keep in mind while approaching a reinforcement learning problem? And you are also aware of what benefits and drawbacks are there for reinforcement learning. Do let me know if, quickly, can you let me know if these takeaways are something that is clear to you? If yes, it would be really, good. Otherwise, please feel free to reach out to me at any point of time. I'll be more than happy to, work it out with you and discuss with you further and try to resolve what queries you may be having. So just to wind up, there are many resources available other than the one that I've shared already. There are ebooks, there are tech talk series, there are documentation, and there is also something known as reinforcement learning on ramp. I'll share this information with you once I get the email IDs. And if you're interested to know what was the progress of that dancing robot that we saw in the first slide, the video. So these robots are a part of Boston Robotics, one of our customers, and they use MATLAB and Simulink to create these robots. The name of the robot is Atlas. Do take a look at these videos and blogs if you're interested to know more about what happened to these. Thank you and have a great day ahead. So I hope I was able to add some value to all of you. And if you are interested and if you want to know more, do reach out to me on this email ID. I hope my email ID is visible on the screen. I will drop it in the chat window also so that you can actually, reach out to me. Thank you so much, everyone. And I'm open to questions now.
Yeah, thank you, Akhil Gobinath. I invite the participants to ask any queries if you have. Participants, if you have any queries, you can ask or you can put it in the chat box. We have running short of time. It's already 3:30. So at least 3 or 4 questions if there. Yeah, sure. Okay. If participants are not asking any doubt, means we can wind up this session. So on behalf of the entire faculty members and the participants and the coordinators, I express my sincere gratitude to Mr. Akhil Gobinath for sharing his valuable information about the hot topic like reinforcement learning. Even though he was so much busy with his work, we have spent 1 hour and 30 minutes. It was a very valuable, very interesting talk. So once again, I thank Mr. Akhil Gobinath on behalf of all the participants and Department of Electrical Engineering. I thank Akhil Gobinath for his valuable time. Thank you so much, sir. Thank you, and we'll meet you again in future. Thank you so much.
Thank you so much, sir, and for this opportunity and the platform.
Thank you.
Do reach out to me, everyone, if you have any questions. And it was a pleasure to be here sharing my information with you. I hope you had a fun learning session and have a good day.
Yeah, thank you so much. Thank you, sir. Participants, you can fill up the feedback form and submit, and we'll meet you tomorrow morning. So thank you so much once again.